So here I just wanted to give a few big picture sort of ideas and an introduction to the kind of models we'll be dealing with in this class, and also contrast them to some of the models you might be aware of, you've seen before, that we're actually not really looking at here. So we're just sort of on the same page. And then we'll delve into them more as we go along. So I basically said that, this is going to be fairly short. I think there will be plenty of time at the end to just talk, so they can ask more specific questions. And then also the materials from some of the last years where the lectures were on that topic were sometimes a bit more detailed. And also the readings. There's a good bit of reading that is basically lecture notes that I converted to hopefully readable articles. So I want to start with the kind of models that we're actually not doing, but that I think a lot of you are probably familiar with. They go by different names. Personally, I prefer the name phenomenological. Non-mechanistic is another one. A common one is statistical, which I don't like too much because the models we'll be talking about can also be used in a statistical manner. But like a lot of stuff you see here, don't get hung up on the terminology. Just look at what it is that you have in front of you, and you kind of know what we're talking about. So here, these kind of models, what I mean by those is anything from a very simple t-test to some complex machine learning or artificial intelligence model like a deep neural network. I'm sure you've used some of them, even if it was just sort of a basic t-test or maybe a linear logistic regression model. So one hallmark of these models is you always use them in conjunction with data. So you have some data and then you apply the model to it. The idea is to kind of see overall, is there a pattern in the data, right? Is there something going on? Sometimes, depending on how you collect the data, you can interpret that, the patterns you see, most of the time the pattern are some sort of correlation in a broadly speaking sense. There's something going on, something associated with something else. Sometimes you can interpret that causally, but not always. You have to be careful about that. One thing these models almost never do is they don't describe the mechanisms by which certain patterns arise that you see. If you've taken a stats class, you've probably heard correlation doesn't imply causation. And that cartoon down there kind of illustrates that idea that, just because two things go up, kind of here in this case, cell phones and cancer, you really cannot say if one causes the other, or they just happen to both go up. So, you get at those patterns, and then from there on, if you want to make further, conclusions, it goes beyond the models. You need to use then your scientific knowledge to decide, oh, does this thing actually cause that or not? So those are the models that I assume all of you have at least at some point played with or been exposed to, and these are the models we will not be talking about in this course. What you can do with these models, a few slides, is in the most basic one, you just describe your data. So you have a collection of data, and then you fit, for instance, here, if you look at this gray line that fits something like a normal curve to it, and you draw a histogram and a box plot. So that's often called descriptive analysis. That's almost always, even if you go beyond that and do a more complex analysis later, usually you start out with kind of summarizing, describing your data. So you start with a descriptive analysis. The next common one is inference. So you have some data, and from that data, you try to infer if there's a general pattern. So in this case, which is not real data, it's made up, but it could be real data. You have how many cigarettes a person smokes a day and their life expectancy, and it looks like there's a negative correlation. So you have some data, and from that, you're trying to conclude that this might be a general pattern in the population. And then maybe, but there are caveats, of course, you can go even one step further and say maybe there's a cause here, maybe cigarettes actually cause the reduction in life expectancy. Though the data and the model itself will never really tell you if there is a causal relation. For that, you need to use outside sort of expert knowledge to conclude that. And prediction, that has really been a growing field. We use predictive models every day, even if we don't necessarily maybe know about it. if you type on your smartphone, your keyboard, and Google or Apple tries to suggest what the next word should be, that's kind of predictive here. Here I went to Google, typed something in the search box, and underneath Google tells me stuff I could do. If you do any kind of translation with Google Translate or something, it's a predictive one. So there's lots and lots of those kind of models that are basically trying to predict based on a whole bunch of data that they ingested, what the most likely wanted answer in this case is, or generally the outcome. Prediction and inference are often related, but they have slightly different, the focus is slightly different. In inference, you usually try to understand what's going on. Underneath, that's the main focus. And how well you predict is maybe secondary, while in prediction, the goal is usually to get as accurate a prediction as possible. And you're okay with the fact that the whole method and algorithm might be a little bit of a black box, that and you're not fully understanding why Google now exactly predicts this. And not only I don't understand, but probably the engineers at Google also don't fully understand, but they're okay with that as long as they have an algorithm that has good predictive power. Again, these are not the models we talk about, so I don't want to go further in detail on those kinds, but just sort of so you get an idea of what they can do. These here are the models we do talk about in this class. These are these models that often called mechanistic models. We've sort of settled a bit on the term simulation models. Sometimes you find mathematical models. And there are all kinds of terminology. Again, don't get hung up on the terminology. The important part is when you see them, you will kind of recognize. The hallmark is that they include mechanisms by which components of the system interact. So in this very simple example, there are just two components. There's the bacteria component and a single immune response component in this very simple model. And they interact, they do things. And they also, so there's interaction part and then there's non-interaction part, but each of them are processes. Now, all these processes are very simplified. So in this example here, you have a growth process by which bacteria grow. Very simplistic. They have an exponential growth, and then when they are getting close to that Bmax value, the growth slows down. It's not, at that level, it's just, okay, this is a mechanism. Now, of course, you could go further and further. There's always many layers where you could say, okay, how does the growth actually work? What happens inside the cell that they happen to divide and so on. So you always have abstractions at some level, but there's some mechanism, even if an abstract one, built into all of those models. And that's why we call them mechanistic models. They're automatically causal because in the model you bake into causes. There's the increase in bacteria is caused by the growth rate or caused by reduction in deaths or bacteria being reduced by the immune response. So you kind of already bake that into the models. So it's there. Almost always, and that's true for the model we'll be looking at, you have some kind of time or dynamic component. So you're tracking how do things change over time. That doesn't have to always be the same. You could have a mechanistic model that doesn't have the time component, but they're fairly rare. And definitely you won't see any of those in this course. Well, all of those will have this dynamic component. How do things change over time? One important thing, and that's a differentiating part to the models I just said we're not discussing here, is you can use those models both with and without data. In that graph that you see at the bottom, there the model is being run without any data. So you give the model starting values, you give values for these parameters of the model, and you just can simulate. You can do that without data. Of course, no data doesn't mean you can be, well, you could if you wanted to be completely free of reality, but usually you want to match your model to the real system. And in this case, you would try to choose the parameters in this model, which would be this G and the Bmax and the dB, such that they resemble the system you're studying. But then you can run it and just explore it without data. And that's often a good starting point with these kind of models. You have a system, a real system that you're interested in. You build one of those models, which is basically an abstraction or simplification of the real system. And then you explore it. You run it for different values. You see what kind of patterns you get out of here. So in this example, you can see two different patterns. There's one pattern with the solid lines where the bacteria and the immune response sort of cycle up and down. Bacteria go up, then that triggers the immune response to grow. It kills the bacteria go down, then the immune response declines, and so on. It goes, in cycles. For another set of parameters, you find something where, the bacteria kind of go up, the immune response goes up, and then both sort of reach a pretty stable level. These are the kind of patterns you can explore and look at. You don't need data for that. And of course, you can apply data to those kind of models. Unfortunately, we won't get too much into that in this course because it's a bit tricky, but here is an example. A simple model here, we have a virus model. We have uninfected cells, so the use, the infected cells, I's, and the virus, the V variable. And we have different processes, uninfected cells and virus meet, that leads to being an infected cell produced, and the infected cells produce virus. That is sort of this P1 here. We'll see that model again, so if you don't fully get it right now, that's okay. We'll revisit it. The point I want to make here is that in this specific model, we have drug. So there's a drug administered in the data that you see here in the symbols. There's one set up without any drug, that's the blue one. And then you have early treatment and late treatment. And so we can ask, well, what's the mechanism by which this drug works? Does the drug reduce the rate at which new uninfected cells become infected? Or does the drug reduce the rate at which infected cells produce virus? Of course, it could be both, or it could be neither. But for this simple example, we have these two. And so in the model, we can then, build that into the model. In this case, this is this E1 and E2. If we had a drug that reduces the rate at which cells become infected, it would act on E1. If it reduces the production of virus, it would act on E2. Then you can compare the model to the data. And the simplest way is comparing just by eye, but most of the time what you do, you would be a more rigorously statistical comparison. You're basically fitting the model to the data, and then that might give you an indication which of those are maybe the more likely ones. So in that sense, with these kind of models, you can do inference like you can do with the more sort of classical statistical models. Here at the same, when you do this, you can test mechanisms because the mechanisms are baked into the models. And you can also use those models for prediction. I'm showing here a population level example because it's something you're all familiar with it. You might have even seen it during the last few years of COVID. There was quite a lot of interest trying to predict, okay, what's going to happen a week, 2 weeks, a month from now. And so at some point, sort of a few months into the COVID pandemic, several teams organized themselves, and the CDC was involved as well, and started regularly publishing forecasts. And so here's from the COVID forecasting hub, basically predictions. I pulled that a few days ago. So you see in solid the actual cases in the US, and then you see in the color different model predictions, what each different model would say will happen over the next so many weeks. As you can see, there's a good bit of variability. So on the EPI level, we're not that great at forecasting yet, and I'd say on the within host level, we haven't even really tried yet. That doing that well is not easy. But you can use those models. Once you have them calibrated, you could run them forward in time and try to predict. There's another type of prediction, which I'm calling here causal exploration, but it has also a predictive flavor. Sometimes you see people call it what-if explorations. So you have your model, and then you change things in your model and see what the model predicts. So in this example, which comes from a 20-year-old paper by Denise Kirshner's group on TB, they built a within-host model for TB, and that model had some of those cytokines in them that Paul just talked about, in this case, IL-10 and IL-4 and IL-12. And then they ran a simulation saying, okay, what would happen if at day 1000, after in the simulated model, chronic infection has established, we would knock out these different cytokines. You can easily do that in the model, right? You just set it to 0 in the model, and then you see what the rest of the model does. So that's a very useful way to explore, what would happen. Now, in this case, it was done not fitting to data, but you could also do those where you have part where you fit it to data, and then you can compare what your results, how they stack up with your predictions. So in this case, you're basically exploring, okay, if I change that, what kind of impact will that have? So, you're doing a cause and outcome simulation. That's another use of these kind of models. So we'll focus on these mechanistic models, and within that sort of, umbrella of mechanistic models, there are a lot of different ones. Agent-based models briefly came up earlier when we had our introductions. In this course, we won't do those kind of models because they're more complex. We'll focus on the simplest kind of models. They're generally called compartmental models. That the name comes from the fact that you have different compartments, basic groupings. And all you do is you check the total numbers in each group. That often corresponds to actually the kind of data you get from immunology, where you do a measurement and you measure the level of IL-10 or the number of T cells. So you have total numbers. And so, you might track how they change over time. And so that's the kind of models we'll be focusing in here. There are two main ways you usually formulate it, either as a differential equation or difference equation. Differential is by far the most common one. I've written it down here as a differential equation. For those of you who are familiar with these kind of models, you see it's a compartment, fairly simple. If you're not so familiar with it, hopefully, by the end of the course, you will have some familiarity. So they're always structured the same way. On the left, you list the compartments you check. In this case, the components we check are bacteria and just a generic immune response, just in one variable. And the dot over it means change with time. Sometimes you also see it notated as dB over dt. I usually just use the shorthand notation with the dot. And then on the right-hand side, it shows you all the different processes or mechanisms that happen in your system. So in this case, we have growth of the bacteria at some rate g. And then initially that's an exponential growth. And then when b gets large and reaches b max, this term in the parentheses, 1 minus b over b max, gets closer and closer to 0. So that means the growth slows down. Then the minus dB by b times b is the rate of decay. So it's basically the rate at which bacteria die. And then the minus kbi term is an interesting one because that's an interaction. So that's the immune response interacting with the bacteria. And in this case, we're assuming they're killing them at that rate k. For the immune response, we have two terms. We have immune response grows at rate r proportional to how many bacteria there are. So if there are more bacteria, you get faster growth, less. And then the immune response just decays at some constant rate independent of how many bacteria those are. Now, for each of those terms, you need to decide how you want to implement it. And we'll get a little bit into that. There are often more than one reasonable way to implement things. And that's then your choice as a modeler, and also the challenge to implement it such that it captures what you know about the underlying biological system reasonably well. You can never get a perfect match because it's way too complicated, the underlying system, but the hope is that if you build it right, it is reasonably close to the real system, that your model will give you answers that are useful in some way. We only have 2.5 days, so of course, in no way is it enough time to get very deep into the modeling, neither is it to get very deep into the immunology. So really our goal here is to give you sort of an overview and introduction, and hopefully set you up with the tools and pointers that you can keep learning on your own. So what we'll do here for the modeling side, we'll play with a few simple models. Most of it will use that R package that I wrote. We'll start with some activities where you don't actually have to write any code. And then at the end, we'll actually look at a bit of code. So if you've never written any code, that's okay. You can, follow along. For those of you that are already really advanced, you can immediately jump in further, downstream and pull out all the code from all of the underlying models and play with it. as I mentioned, fitting models to data is something that's really interesting, and I know a lot of students always would like to do it. Unfortunately, it just in 2.5 days, it's just not enough to cover that and not, lose the majority of students going along. I've done it in the past, but it's always the most technically complex one. That said, if you really want to do it in the R package, in the DSA-RM, there are several apps in there that do fitting. So go there, explore them, and definitely feel free to ask me any questions on those, and I'll be happy to, answer any fitting questions that you might have if this is of special interest to you. Okay, and that was my fairly brief go through those. And at this point, we can just keep talking, answering questions, anything you have based on what I said so far, or anything generally about the modeling part.